Hi, my name is Annalisa Baronetto. I am a researcher at the Chair of Digital Health. Welcome to our presentation on simulation of garment-embedded contact sensor performance under motion dynamics. Smart garment can support long-term health monitoring in everyday life. Contact sensors like electrodes and microphone highly depend on correct positioning and garment fitting. In this work, we present a novel simulation method to estimate contact sensor performance during different motion sequences that may occur during activities of daily living. So far, the analysis has only been conducted in static body positions. Our method comprises 4 steps: 3D human body model generation, automated smart garment design, simulation of activities of daily living, and dynamic sensor fitting and displacement evaluation. The open source SIMPLE model was used to generate rigged human body models. SIMPLE is a human model whose body pose and shape was learned from 3D human real scans, including the CESAR dataset. In total, we generated a dataset of 100 models of different body shape and sex. The obtained 3D human body models were animated with motion capture data from the AMAS and CAPE dataset. 6 motion sequences, including ADS like walking and drinking, were simulated in our analysis. The model TaylorNet was used to dress the 3D human models during the simulation. TaylorNet is a cloth model reconstructed from images and 3D scans, whose fabric deformation was learned from physical-based simulations. The model provides different garment designs, including 24 different t-shirts. From TaylorNet, we selected 3 different t-shirt styles with different fitting. All the used t-shirts were made of stretchable fabric. To evaluate the sensor performance, we consider an ECG measurement application and define the electrode's location on the cloth models according to the 12-lead ECG standard. Body sensing errors can be influenced by 2 factors. First, the body garment distance may vary during the motion. The garment may detach from the body and the sensor may no longer be in contact. Second, the garment may slide on the body surface due to the body segment motion, and the sensor may be displaced from the intended measurement positions. We evaluated the garment distance and displacement for each cloth vertex. Before the evaluation, a calibration was done to find the point-to-point correspondence between the cloth and the body models. The results show the distance errors decrease with larger BMIs for both sexes. The used cloth model is indeed unisex and is not fully personalized to fit the different body shapes. Sensors below the breast show higher distance errors, mostly because of the larger body shape variability. Males show higher displacement error variance than females. Electrodes below the neck are on average less misaligned than the other sensor, especially the electrodes on the lower abdomen. The higher displacement could have been caused by arm lifting movements. Overall, the sensors below the neck show the smallest distance and displacement, whereas the sensors below the breast show the highest distance values, and the sensor on the abdomen show the highest displacement values. Housework works and lifting a box show the largest distance ranges, probably because of the higher complexity of the movement. Female models present smaller sensor displacement than males. The female different body shape could have decreased the possible displacement of the garment. We compared the results of our simulation with ECG shirt measurements found in literature. According to the previous studies, the optimal electrode position is below the breast. In our analysis, although sensors below the neck and next to the sternum show slightly lower displacement, they tend to lose contact with the skin more easily than the sensors below the breast. The results are therefore in agreement with literature. In conclusion, we presented a novel method for simulation and performance analysis of contact sensors embedded in smart garments. We were able to show the performance changes as a function of body shape, garment fit, and movement type. In further work, we plan to extend the existing method to include fabric properties and garment cuts, as well as other sensor modalities, such as orientation and strength sensors. For more information on our work, check our conference paper or contact me. Thank you for your attention. I wish you a great time at this year's conference.